In this lesson, I just wanted to give some more practice with exponential decay, and more specifically solving for our rate k. If you were just watching Professor Messenger's video, you'll note that he used r. It's important really just to understand that when you go between your textbook and this lesson and Professor Messenger's video, that the equations a equals a sub 0 e to the kt, a of t equals a sub 0 e to the kt, and then what Professor Messenger used, a equals a sub 0 e to the rt, are all equivalent forms of your exponential growth and decay model. So really the only difference between what Professor Messenger used and your textbook and what I will use would be that he used r for your rate rather than k. Alright, so we're still solving for the same thing. So in this problem, we have the half-life of strontium-90 is 28 years. Suppose that a nuclear accident occurs and releases 60 grams of strontium-90 into the atmosphere. We want to find the rate of decay, K, for strontium-90. So if we think about this, first we want to understand that at T equals 0, as soon as the nuclear accident occurred, we had 60 grams of strontium-90. Now, what we know about the half-life of strontium-90 is that it's going to take 28 years for half of it to decay. So that means that at t equals 28, we would have half of that original amount, which means we're going to be taking half of 60. Well, half of 60 is just equal to 30. So at t equals 28, we would have 30 grams of strontium-90. So in order to find K, we have that our A sub 0, our original amount, was 60 grams. For T equal to 28, we had an A that was equal to 30 grams. So this means that if I'm substituting into one of our formulas, I'll use the A equals A sub 0 e to the kt. We're going to end up with A was 30. A sub 0 is 60, and then e to the k, that's what we're trying to find, times t, which is 28. And again, we can rewrite this as 30 equals 60 e to the k times 28. We can rewrite as 28k. And then this way we have an equation, an exponential equation that we can solve for k with. Now that we have an exponential equation, we can solve for k. So in order to solve for k here, I would need to isolate our exponential. So right now I have 30 equals 60 e to the 28k. Well, I'm going to divide both sides by the 60 in order to isolate the exponential. On the left-hand side, 30 over 60 would reduce to 1/2, so I have 1/2 or 0.5 equals e to the 28k. So if we look at what we have here, that 1/2 is significant because that comes from that idea of half-life, is that after 28 years, we started off with 60 grams, we took half of it, so we'd be left with half the amount, which was 30. Anytime we're solving for k with half-life problems, we're always going to get this 1/2 here because we're trying to find half of the original amount. So what we could have done is we actually could have started our equation in solving for k right here. So from this point on, if you wanted to start here, that is perfectly fine. Because we're saying that we have half of whatever the original amount was is going to equal e to your half-life time, the number of years it takes to get half of your amount, times your k, which is what we're trying to find, the rate of decay. So it's okay that we actually could have started here as long as you understand where it comes from. At this point then, we're going to want to take we want to solve for k, and in order to do so, we want to take the natural log of both sides since we have that natural base. It'll make our lives a little bit easier. So I'm going to have the natural log, I'll rewrite 1/2 as 0.5 now, but you can keep it 1/2 if you want, equals the natural log of e to the 28k. Remember using our log property on the right-hand side that the natural log of e raised to some exponent. The exponent comes down and the natural log of e is just 1. So we actually have the natural log of 0.5 equals 28k. From here then we just have one last step in order to solve for k. We need to divide both sides by 28. So we will end up with an exact answer of k equals the natural log of 0.5 over 28. Again, we want to keep this exact answer unless we're told to round. I'm going to keep this throughout the rest of the problem, but if you did want to put this in your calculator, again, remembering to be careful with your parentheses, you should get an approximate value of k is negative 0.024755526. But again, I'm going to keep that k for the next part of the problem. So what this shows is our rate of decay. Your k is negative because we're decaying, so we have a less amount than what we started with. Now that we've found our k, we can find the exponential decay model for strontium-90 based on starting with that 60 grams of strontium-90. So we want to go back to the general formula of A equals A sub 0 e to the kt. Our A sub 0 was the amount of strontium that we started with, so we had A sub 0 equals 60 grams. We found in our first part that k was equal to the natural log of 0.5 all over 28. And what happens with that exponential decay model then is that we want to just fill that information in. So we're going to keep A is going to stay A sub 0 is going to become 60, e to our k, which is natural log of 0.5 over 28, and then times by t. Because what this does is that it allows us to find how much strontium-90 is left after t years. So if we're given the number of years, we can just substitute in. And what it also allows us to do is if we know the amount of strontium-90 that we have left, we can figure out how long ago the strontium-90 was originally let out into the atmosphere. So something like this is important for carbon dating. When archaeologists find some ancient artifacts, they want to figure out how old it is. They'll take a sample and figure out how much carbon-14 is left, and then they'll be able to use a formula similar to this and date it back using the rate for carbon-14. So this right here is your exponential decay model for strontium-90. It's just saying, okay, using what we got for K, what's our general formula to use? As I was just saying on the previous slides, now that we have our exponential decay model for strontium-90, we can figure out how long it will take for that 60 grams to decay to a level of 10 grams. So what we have here then is that we have the amount, that's our A. So we have that A is equal to 10, and we're trying to figure out how long, which means we're trying to figure out what T is. So I'm just going to substitute into this equation, and then we're going to solve for T. So A is 10 equals 60 e to the natural log of 0.5 over 28, and then we're trying to solve for t. So essentially we're going to be following very similar steps that we just did in part A when we're trying to find k. We need to isolate the exponential first, so I'm going to have to divide both sides by that 60. So when I divide by 60, I'm going to end up with 10 over 60 equals e to the natural log of 0.5 all over 28t. But 10 over 60 we can rewrite as just 1/6 equals e to the natural log of 0.5 over 28 times t. So that's just isolating e. At this point, we want to continue to solve for t. In order to do so, again, this is an exponential equation, so we need to be taking the natural log of both sides. So we'll be taking the natural log of 1/6 equals the natural log of e to the natural log of 0.5 over 28t. Again, using that natural log property is that the natural log of e will essentially go away and the exponent will drop down, so that we just have the natural log of 1/6 equals the natural log of 0.5 over 28t. Another quick note is that 1/6 is a repeating decimal. You don't want to change it to a decimal yet until it tells us to, which is usually at the end. So if you round too soon, then your answer will be a little bit off. So since 1/6 is the repeating decimal, I'm going to have to keep 1/6 throughout. At this point, we need to continue to solve for t. So on the right-hand side, I have a fraction times t. Remember, in order to get rid of a fraction that's being multiplied, you can multiply both sides by the reciprocal. So that's what I'm going to end up doing here, is I'm going to times both sides by 28 over the natural log of 0.5. So then that way on the right hand side, your fractions will end up canceling out. On the left hand side, we can rewrite this as 1 fraction to be 28 natural log of 1/6 over natural log of 0.5, which would be equal to t. So again, that would be your exact answer, but not very helpful to us. So we do want to type this into your calculator to get an approximation. When you type in your calculator, remember, again, watch your parentheses. You're going to put the entire numerator in parentheses, the entire denominator in parentheses. If you hit natural log and it opens a parenthesis, just make sure that you close it. So when we do so, we should get an approximate answer of about 72.37895,002, or we can say that t is about 72 years. So it would take about 72 years in order for 60 grams of strontium-90 to decay to 10 grams. And you do want to sort of think of this in a logical manner. If it takes 28 years for 60 grams to decay to 30 grams, we need to get to 10 grams. Another 28 years would take it to go from 30 grams to 15 grams. That means that it would take 56 years to get down to 15 grams. Another 28 years would be to take it from 15 grams to 7.5 grams. Well, that would bring us to 84 years. So between 56 years and 84 years, we're decaying from 15 grams to 7.5 grams. So 10 grams would be between that. So it does make sense that the 72 years is somewhere between the 56 years and the 84 years.